we can use Newton's law, his law of gravitation, and his second law to deduce a relationship between orbital radius and orbital period for the planets in the solar system. All the planets in the solar system um, go around the Sun. The Sun is at the center. M sub s is the mass of the Sun. In orbits that are pretty close to circular. Technically, that's not true. They're elliptical, but for purposes of this discussion, I'm going to assume they're circular, which is a pretty close approximation. And the distance of the Earth from the Sun, it has a special unit called an astronomical unit. One astronomical unit is that distance, which is 1.5 times 10 to the 11th meters. It's 150 million kilometers. Um, so we we know from the gravitational law that force of the Sun on the Earth is going to be big G times the mass of the Sun times the mass of the Earth divided by the distance between them squared. This is 1 AU for the Earth-Sun distance. On the other hand, from Newton's second law, we know that the acceleration of the Earth is going to be this divided by the mass of the Earth. And so that's going to be big G times the mass of the Sun divided by the distance squared. But because Earth is executing UCM, we know that the acceleration will also be d times omega squared, because d is the essentially the radius of the Earth's orbit, and omega is the angular frequency, and we can express omega in terms of period by realizing that omega is equal to 2 pi over t. And so I've made that connection here, done some simplification, and then from here to here now I've done some algebra. And so I've gotten all the variables over on the left-hand side of the equal sign. T squared over d cubed, so t is period, d is the orbital radius, is a constant. It's 4 pi squared divided by big G times the mass of the Sun. And so if you put the numbers in and figure that out, it's 3 times 10 to the minus 19. And I'm not writing the units out here, but I'm using standard kilograms, meters, second units. And so for the Earth, T is 365.24 days, which by converting to seconds, there are 24 times 3600 seconds per day. And D is 1 AU, which, as I said above, is 1.5 times 10 to the 11th. And if you compute this ratio, you actually do get 3 times 10 to the minus 19. And this is actually known as Kepler's one of Kepler's laws. This is Kepler was a mathematical prodigy, genius, who helped Tycho Brahe with his data and made some important deductions, which Newton then later explained in a more fundamental way. And so some pointers on this. Since this is a constant, since t squared over d cubed is a constant, this number right here, this ratio, it's the same for all planets in the solar system. And so we showed that for Earth it's true, but it's true for the other planets as well. And so here's some things you can do, skipping down to number 2 first, because that's a direct segue to what I was just talking about. If you knew that the period for Mars was 687 years, it took 687 years for Mars to make a full revolution about the Sun. Use this expression that we have up here to compute Mars's orbit, and then compare it with what you find on the internet. Okay, number 2 is what is Earth's orbital speed? from the data that we have up here, you should be able to figure that out. So there's two little mini problems for you coming out of this YouTube.